Hello everyone, I welcome you all for the second session of the chapter Wave Optics. In today's class, we will be learning about the coherent and incoherent addition of waves and also the theory of interference. First, let me start with the principle of superposition of waves. Principle of superposition of waves. So this has been already learnt in your first PUC physics. Okay? Principle of superposition of waves. So what is the statement of principle of superposition of waves says? It states that when two or more waves acting at a point simultaneously, the resultant displacement produced by the waves will be equal to vector sum of the displacements due to the individual waves. Suppose if I consider two waves are acting at a point simultaneously at this point. Say that this is the displacement and this is the time. So due to this superimposition of waves, the resultant wave will looks like this. It increases its amplitude. Okay. So the resultant displacement y will be equal to, if I say the displacement of the first wave is y1 and the displacement of the second wave is y2, then the resultant displacement of this wave will be equal to y is equal to y1 plus y2 vectorially. Okay. When two or more waves are simultaneously acting at a point, then the resultant wave will be having a displacement equal to the vector sum of the displacements due to individual waves. So this has been learned already in your first PUC. Now in this class, let us understand how the two light waves are going to interfere on each other or superimpose on each other. So for this, first we need to understand what is a coherent sources. Okay, what are coherent sources? If we say the two sources, say this is S1 and this is S2, which are emitting the waves in all the directions, and say this is the light emitted by the source S1 and this is the light emitted by the source S2. P is the point where the two waves are meeting at a point. So the two sources are said to be a coherent sources whenever they emit the light waves which are having a same frequency and zero or constant phase difference. So how do we understand this one? See, if the two waves are acting at a point, say this is a one wave, this is the first wave, the displacement of this wave is y1 is equal to a sine omega t. Okay, this is time t and this is displacement y, where a is the amplitude of the wave. And we have one more wave which is falling on this wave in this manner. Say this is the second wave which is having a displacement of y2, and this y2 can be written as, I will say this is a1. For the first wave the amplitude is a1, for the second wave amplitude is a2 and sine of omega t plus phi, but this phi is, where this phi is known as a phase difference. In this case the two waves, this one and this one, are having a zero phase difference, correct? The state of vibration of both the waves are same, that is why the phase difference is zero. Therefore I will drop this off. Therefore we can represent the second wave like this. Okay, so these are the two waves which are in phase or they are having a zero phase difference. Next, if I consider one more case here, say this is the first wave which is having y1 is equal to a1 sine omega t, and one more wave which is falling on this wave which is interfering like this. Okay, this is the second wave, y2 is equal to a2 into sine of omega t plus phi. But in this case the phi is not equal to 0, correct? Phi is not equal to 0. They are having some phase difference. How do we express this phase difference? The phase difference between these two waves will be equal to pi. Suppose if the origin of this wave is somewhere here, okay, origin of the wave is somewhere here, for this wave the origin is somewhere here, so this is lagging by a phase of pi. That is why the phase difference between this wave and this wave is equal to pi. So we can write this phi is equal to pi now. Now these two waves are having a constant phase difference of pi between them. So this has already been learnt in our previous sections. The two sources are said to be a coherent sources if they emit the light with the same frequency, and very importantly they must be having a zero phase difference like this, or they must be having a constant phase difference. In this case the phase difference is 0, but in this case the phase difference is equal to pi, which is a constant one. Now what is interference of light? So that we have to learn now. Let me write what are coherent sources. So this is how we define the coherent sources. The sources are said to be the coherent sources if they emit the light having same frequency and zero or constant phase difference. Now what is interference of light? The phenomenon of interference of light is defined as the phenomenon of redistribution of light energy in a region due to the superimposition of two or more waves emitted by the coherent sources. So this is how we define the interference of light. The phenomenon of redistribution of light energy in a region where the two or more light waves are superimposing on each other, or they are falling on each other, as we have learnt in the addition of waves. See, when the two waves, say for example the two waves are falling like this, they are superimposing on like this. So these are the waves emitted by the two coherent sources, because they are having a same frequency and constant phase difference, correct? Or zero phase difference in this case. So when these two waves are interfere each other, what happens is the light energy is going to increase its intensity like this. Okay, so there is an increase in the intensity of that light wave. So in this region the two light waves are superimposing on each other, therefore the resultant displacement increases, hence the intensity at that region will increase. So this phenomenon is nothing but a interference of light. So in case of interference, there is a redistribution of light energy or redistribution of light intensity at a region where the two or more waves are interfering on each other. So this is one type of interference which is called as a constructive interference. So in case of constructive interference, the crest of one wave is falling on the crest of the other wave and trough is falling on the trough, so that the resultant amplitude increases, hence its intensity also increases. Now we have one more type of interference where what happens to the waves are, see, the two waves are interfering on each other like this. Okay, the two waves are interfering on each other like this. This is the first wave and this one is the second wave. See, in this case the phase difference is equal to pi, correct? They are having a constant phase difference of pi. Means the crest of one wave is falling on the trough of another and the trough is falling on the crest of the second wave. So in this case, what happens to the resultant intensity? The resultant intensity is going to decrease and the amplitude is decreasing, therefore the intensity at that region will decrease. Okay, so this happens in case of a destructive interference. This is called as destructive interference. So there are two types of interference. The first one is called as a constructive interference and the second one is known as a destructive interference. Let me write that. Types of interference. So as I explained you, in case of constructive interference, how does the light waves interfere? So the two waves are like this. So due to this superimposition, what happens to the resultant wave? It increases its amplitude and hence the light energy, the light intensity at this region will increase. So this is constructive interference. And we have destructive interference. And in case of destructive interference, what happens is the two waves are interfering on each other like this. Okay, the two waves are interfering on each other like this, so that there will be a decrease in intensity and the resultant wave decreases its amplitude, and hence in this region the intensity of the wave will decrease. So this is the two types of interference we have, constructive interference and destructive interference. Now we'll be moving on to the very important topic, that is a theory of interference, and using that we need to write the conditions for the constructive interference as well as a destructive interference. Okay, so theory of interference. Under this topic we will be learning the derivation of condition for the constructive interference as well as the destructive interference, which will be asked for 5 marks in your examination. So be very careful with this. First, let us start with consider two coherent sources. As I told you, for the case of interference, the sources must be a coherent source. Two coherent sources emitting the light waves of displacements y1 is equal to a sine omega t and y2 is equal to a sine omega t plus phi. Say we have two coherent sources which are emitting the light waves, and the displacements of the waves are given by y1 is equal to a sine omega t and y2 is equal to a sine omega t plus phi, and these two waves are going to interfere. Say that S1 is the first source, and S2 is the second source which are emitting the light in this direction. Say this is y1 and this is y2, and they are interfering at the point P. Now, using principle of superposition of waves, I have explained you that according to the principle of superposition of waves, if two or more waves are meeting at a point, then the resultant displacement at this point is equal to the vector sum of the displacements due to individual waves. If these are the displacements of the two waves, then the resultant displacement is equal to y1 plus y2. Y is equal to y1 plus y2, where y is the resultant displacement at this point where the two waves are interfering on each other. So let me write what are y1 and y2 now. y1 is equal to a sine omega t plus y2 is equal to a sine omega t plus phi, where this phi is known as a phase difference, where phi is called as a phase difference. Now let me take a common here. So y is equal to, now in these two terms, the term a is constant, so let me take it out. Y is equal to a into sine of omega t plus sine of omega t plus phi, correct? So we got this expression. Now if you look at this one, this equation is in the form of sine c plus sine d, correct? Where in place of c we have omega t and in place of d we have omega t plus phi. So sine c plus sine d, that will be equal to 2 into sine of c plus d by 2 into cos of c minus d by 2. So this is a formula for sine c plus sine d, and we can write this term like this. Okay, 2 into sine of c plus d by 2 into cos of c minus d by 2. Now we can write this expression in this form. So let us write this. Y is equal to a into sine c plus sine d. It is 2 into sine of c plus d by 2. Therefore 2 into sine of c plus d. C is omega t plus d is omega t plus phi by omega t plus phi. So this whole divided by 2 into cos of c minus d by 2. C is again omega t minus, this is d, omega t minus phi, correct? Whole divided by 2. Now further rearrange this. Y is equal to a into 2 sine of omega t plus omega t is 2 omega t. 2 omega t by 2 is omega t only. Therefore this will be omega t plus, this is phi by 2. correct? Next, cos of, here omega t and omega t gets cancelled, cos of minus 5 by 2 remains. This is cos of minus 5 by 2. Now let us write this equation as y is equal to 2a into cos of minus 5 by 2, that into sine omega t plus 5 by 2, correct? So we got this expression now. Now this 2 is a constant, a is a constant, and phi is a phase difference, which is a constant for a coherent sources. Therefore we can write this whole term to be equal to some r. So r is a resultant amplitude. So this is nothing but an amplitude of the wave. The constant is nothing but an amplitude of the wave. So we can call this amplitude of the resultant wave is equal to r. Therefore this will be r into sine of omega t plus 5 by 2. So now take this as equation number 1. So that equation number 1 gives the resultant displacement at this point due to the interference of these two waves. Okay, now we need to understand, so at this point P, what is the condition for obtaining the constructive interference and what is the condition for obtaining the destructive interference? That we need to understand now. Okay, let's see this. Now that equation number 1 gives the displacement of the resultant wave. If I naught is the intensity of the individual wave, okay, so I said that from the coherent sources S1 and S2, the waves are interfering at that point, this point P, and we write the displacement of the one wave as a sine omega t, where a is the amplitude of the individual wave. So if I naught is the intensity of the individual wave, then this I naught is directly proportional to the square of the amplitude. The intensity of any wave is always proportional to the square of its amplitude. So if I naught is the intensity of the individual wave, then it is proportional to the a square, correct? Next, let I be the intensity of resultant wave, then I is proportional to the square of the amplitude. So from this equation, this term which is written as r, this becomes an amplitude. Therefore the intensity of the resultant wave is proportional to the square of that term r. Therefore this is proportional to r square. But I know that what is r square? R square is equal to 2a into cos 5 by 2. So this I is proportional to 2a into cos of minus 5 by 2. Okay? But according to trigonometry, we know that cos of minus theta is equal to cos theta, correct? Cos of minus theta is equal to cos theta. Therefore, we can write this cos of minus 5 by 2 as cos 5 by 2, correct? Therefore, I is proportional to 2a into cos 5 by 2. Okay? So actually this is square. So let us write a square here. This is whole square, correct? So we got intensity is proportional to 2a cos 5 by 2 the whole square. Now this is written as I is proportional to 4a square into cos square 5 by 2, correct? 4a square into cos square 5 by 2. The proportional constant for this one and this one is same. Therefore, if I divide these two equations, okay, let me divide I by I naught. Now, if I divide this I and I naught, what we will get is I divided by I naught is equal to I naught, I is this 4a square cos square 5 by 2 divided by that term is a square. So, a square and a square gets cancelled and I is equal to 4 cos square 5 by 2 into this term I naught. Therefore, intensity is equal to 4 cos square 5 by 2 into I naught. Or we can write this as I is equal to 4 I naught into cos square phi by 2. Okay, this is the intensity of the resultant wave at this point. Okay, intensity of the resultant wave at this point. Now, a very important part of this derivation, we need to write the condition for the constructive interference. Constructive interference. Let us write this. Condition for constructive interference. Now, let us write the condition for constructive interference. See, I told you that in case of constructive interference, due to the superposition of waves at this region, the intensity has to be maximum. Okay, intensity has to be maximum, which means this term, if I say this is equation number 2, so in this equation number 2, the intensity has to be maximum for the case of constructive interference. So at the point P, if I want to get the maximum intensity, this term has to be maximum. For intensity to be maximum, cos square phi by 2 is equal to 1, correct? Because the value of cos will be maximum if it is equal to 1. Therefore, if this term has to be maximum, this term should be equal to 1. Okay? Then cos square phi by 2 is equal to some plus or minus 1. So if this cos square phi by 2 is equal to 1 means the value of pi by 2 should be equal to integral multiples of pi. Then only this value is equal to plus or minus 1, correct? Or the phase difference phi. If I take 2 to this side, you will get 2n pi, correct? 2n pi. Means if I have the values of phi is equal to 0, 2 pi, 4 pi, etc. So if the values of phi is equal to 0, 2 pi, 4 pi, 6 pi, even multiples of pi. Okay, if the value of phase difference is even multiples of pi, this term will be equal to 1 and we get the constructive interference and the intensity at the point P becomes maximum. Okay, therefore the phase difference is equal to this much. Now let us write this in terms of a path difference. Okay, how do you write the path difference? Path difference is equal to delta x. Delta x is equal to lambda by 2 pi into phase difference phi. So if I write this condition, so delta x is equal to lambda by 2 pi into phi. Therefore delta x is equal to lambda by 2 pi into the phase difference must be equal to 2n pi. Therefore if I write this as 2n pi, we get 2 pi. 2 pi and 2 pi gets cancelled. So delta x is equal to n into lambda. Therefore n is equal to n is equal to 0, 1, 2, 3, etc. So if I want the constructive interference, that is the intensity should be maximum, we need to get a path difference is equal to integral multiples of lambda, a wavelength. Okay, integral multiples of wavelength. Then we get the condition for constructive interference. So in the examination they will ask like this: give the theory of interference and obtain the condition for the constructive interference in terms of path difference. So what is the answer? So first we need to derive this equation. Okay, from the starting, if I consider y1 and y2 are the displacements of the two waves, then up to this we have to derive. Now next, for the condition of the constructive interference, in order to get a constructive interference at the point P, what is the phase difference? Phase difference is equal to 2n pi, and then you have to write the path difference as lambda by 2 pi into phase difference. So phase difference is 2n pi, and finally we obtain the path difference is equal to n into lambda, where n is equal to 0, 1, 2, 3 up to infinity. Delta x is equal to n lambda is the condition for the constructive interference, where the resultant amplitude is maximum as well as the intensity is maximum. Now we have to write the condition for destructive interference. So after writing this, you have to write this is the condition for delta x is equal to n lambda. So this is the condition for constructive interference. Okay, after obtaining this expression, you have to write this one. Now let us write the destructive interference. In order to get the destructive interference, the intensity has to be minimum or it will be equal to 0. So say if we have sources S1 and S2 and the two waves are emitted here, and at this point P, if the intensity has to be minimum, then we have to get this intensity must be equal to 0. Okay. How do we make that intensity to be 0? If intensity is to be minimum, minimum means I is equal to 0. So how do we make this I is equal to 0? This cos square phi by 2 must be equal to 0. Therefore, cos square phi by 2 will be equal to 0. For this condition to satisfy, the value of phi by 2 must be equal to pi by 2, 3 pi by 2, 5 pi by 2, etc. Correct? So the values of phi by 2, this phi by 2, the angle will be equal to pi by 2, 3 pi by 2, 5 pi by 2 likewise. Then only we get the cos value of 0. Now, to get this one as 0, the value of phi by 2 should be pi by 2, 3 pi by 2, 5 pi by 2 likewise. Or, the value of phi should be equal to, if I cancel 2 on either side, then we get pi, 3 pi, 5 pi, etc. Means, if I want to get in general, the phi is equal to 2n plus 1 into pi. Okay, odd multiples of pi. In the previous one, we get even multiples of pi. Now we get odd multiples of pi as a phase difference to get the intensity to be 0. Now, let us write this in terms of a path difference. So, in terms of path difference is equal to delta x, that is equal to lambda by 2 pi into phase difference phi. So, if I write this, delta x is equal to lambda by 2 pi into, what is the phase difference? Phase difference is equal to 2n plus 1 into pi. So this is 2n plus 1 into pi. Now cancel this pi and pi on either side. Therefore, delta x is equal to 2n plus 1 into lambda by 2. So now we get an expression for the path length in case of a destructive interference. So where this n is equal to 1, 2, 3, etc. up to infinity. So this n is equal to integers like 1, 2, 3, 4, 5. So in this case we get a destructive interference. So at this point P, now the intensity will be minimum or it will be 0 when the path difference is equal to 2n plus 1 into lambda by 2. Let us write this. This is the condition for destructive interference. So in this class, we deduce the theory of interference and we obtain an expression for the resultant intensity as I is equal to 4 I naught into cos square phi by 2. So using that, we deduce the condition for the constructive interference as well as the destructive interference. We write an expression for the path difference for the case of constructive interference as well as in the case of destructive interference. That will be the end of the session. The next session, we will be learning a very important one, Young's double slit experiment. Until then, thank you.